Today, we are looking at something truly special. We're not just explaining a new idea, we are bearing witness to what might just be one of the most significant breakthroughs in the entire history of science, a framework that promises to unite the whole cosmos under a single, unbelievably elegant principle. For over a century, this has been the absolute holy grail of physics, a single theory that describes everything from the tiniest quantum particle buzzing in and out of existence to the largest galaxy spinning in the void. And now, the question isn't just hypothetical anymore. A groundbreaking new paper suggests the answer might finally be yes. This monumental work comes to us from two physicists, Alexander Ngu and Amaya Odilon Kosso. And what they've proposed, it's nothing short of a complete reimagining of reality itself. We're talking about a potential Nobel Prize-winning theory that could be the master key to unlocking the universe's deepest, most stubborn secrets. All right, so here's our roadmap for this journey. First, we're going to look at the great divide in physics that this theory is trying to heal. Then we'll dive into the core concept, something called the delta infinity Omicron transformation. After that, we'll see the proof, how unification at the Planck scale makes it all click. Then the fun part, how this framework solves some of physics's greatest paradoxes. And finally, we'll look at the future of reality and the predictions we can actually go out and test. So, to really appreciate just how massive this discovery is, we first have to understand the problem it's solving. You see, for the last 100 years, physics has spoken with a split tongue. It describes the universe using two completely incompatible languages. On one side, you've got quantum mechanics. This is the bizarre, fuzzy language of the very small. It's all about probability, chance, and it describes three of the four fundamental forces. On the other side, you've got general relativity, Einstein's masterpiece. This is the language of the very large, planets, stars, galaxies. It's governed by the smooth, predictable geometry of spacetime, and it describes gravity. The problem? They just don't work together, at all. They're fundamentally incompatible, which means they can't both be the final word. There has to be a deeper language that unites them. And this is where Ngu and Kosso come in. They propose that there is a master key, a single, transformational principle that shows quantum mechanics and general relativity aren't two different languages at all, but just two different dialects of a much more fundamental universal grammar. They call it the delta infinity Omicron framework. So, what is this principle, really? At its heart, it's a simple but incredibly profound idea about how things change. I want you to picture a triangle. Now imagine adding more and more sides. A square, a pentagon, a hexagon. Keep going, adding an infinite number of tiny sides. What do you eventually get? A perfect circle. This process, transforming a sharp, distinct shape into a smooth, continuous one by going through infinity, that is the core analogy for this entire framework. Okay, let's break that down. The triangle, delta, represents the quantum world. This is the realm of pure potential, of the fuzzy and the probabilistic. Think of it as a particle that could be here, or there, or anywhere, a field of pure possibility. So, how do we get from that fuzzy possibility to a concrete reality? Well, that's where infinity comes in. In this framework, infinity isn't just a concept. It acts as a kind of universal translator. It's the engine of transformation, the bridge that connects the quantum world to our classical world. And the theory proposes this bridge exists at the tiniest possible scale in the universe, the Planck scale. And this brings us to the final stage, the circle, or Omicron. This represents the classical reality we actually see and measure. It's the world of definite outcomes where a particle has a specific location and gravity curves spacetime in a nice, predictable way. The potential, the delta, has finally become actual, the Omicron. Let's see how this pattern actually shows up in quantum mechanics. A particle's potential states, all the places it could be, are described by something called the wave function. Think of this as our delta, just pure possibility. Then, when we measure it, a fundamental constant of nature, Planck's constant, acts like that infinity mediator. The wave of possibilities collapses into a single, definite outcome. And that's our Omicron, the reality we can actually measure. Now get ready for the truly breathtaking part. The theory shows that general relativity follows the exact same pattern. The presence of matter and energy, which is the source of gravity, that's our delta. It's the potential for space-time to curve. Then, Einstein's equations, with their own set of fundamental constants, act as the infinity mediator. They transform that potential into the actual measurable curvature of space-time that we experience as gravity, our Omicron. It's the same deep structure, just playing out in a different context. Okay, a powerful analogy is one thing, but physics demands proof. If both theories really are just dialects of the same language, they have to converge somewhere. And New and Kosso show that they do, at the most fundamental level of reality you can possibly imagine, the Planck scale. The Planck scale is the universe's absolute ground floor, the shortest possible length, the briefest possible moment in time. What's so crucial is how these units are calculated. You see, they're forged from the three great constants of nature: h bar from the quantum world, g from gravity, and c, the speed of light, which connects everything. This isn't a coincidence. It's the natural battleground where quantum mechanics and gravity have to finally meet. So let's start with the quantum side. Heisenberg's uncertainty principle basically says the more you pin down a particle's location, the more uncertain its momentum, or its energy, becomes. So what happens if you try to squeeze a particle into the absolute smallest space possible, the Planck length? Well, the math shows this gives the particle a very specific minimum amount of energy, an energy that is directly related to something called the Planck mass. Okay, now let's look at gravity. We know a black hole is formed when you pack enough mass into a small enough space. Einstein's equations tell us exactly how much mass is needed. So what's the smallest possible black hole you can make? Well, it would be one whose radius is just a single Planck length. And when you calculate the mass needed to do that, the answer is just astonishing. It's the exact same amount of energy we just found from the quantum side. And here it is, the beautiful conclusion. At the absolute limit of reality, the energy demanded by quantum mechanics to confine a particle perfectly matches the energy demanded by general relativity to collapse that same particle into a tiny black hole. The quantum limit and the gravitational limit are one and the same. The two supposedly incompatible theories, they aren't just speaking the same language. At this fundamental level, they are saying the exact same thing. A beautiful theory is one thing, but a powerful theory has to solve problems, and the delta infinity Omicron framework elegantly resolves some of the most profound, most persistent paradoxes that have haunted physics for decades. So let's start with the biggest question of them all. Traditional physics tells us the universe began with a singularity, this theoretical point of infinite density where all the known laws of physics just break. The theory literally can't tell us what happened at time zero or what might have come before. This new framework completely replaces that problematic singularity with something far more elegant, a quantum bounce. Instead of infinite curvature, space-time curvature reaches a maximum but finite value at the Planck scale. Physics doesn't break down at all. Instead, the universe acts like a kind of quantum trampoline, smoothly transitioning from a previous, contracting state into our current, expanding one. There was no beginning of time, just a seamless transformation. And the solutions just keep coming. It tackles the famous black hole information paradox, suggesting information isn't actually destroyed when it falls into a black hole, but is safely stored in tiny quantum corrections to spacetime. It also resolves the problem of time, this weird quirk where time seems to vanish in some quantum equations. In this new view, time isn't fundamental at all. It's an emergent property of this constant transformation of the universe, from possibility into reality. Now, this is not just some philosophical or mathematical abstraction. The real power of Ngu and Kosso's work is that it makes concrete, falsifiable predictions. It gives us an actual roadmap to test whether this beautiful idea is, in fact, the true nature of reality. The framework predicts that if we could get to really high energies, the Heisenberg uncertainty principle itself should change slightly. It predicts tiny, specific deviations in the cosmic microwave background, the afterglow of the big bounce. It suggests we might even detect echoes in gravitational waves from merging black holes that could hint at this deeper quantum structure. These are all real signals that we can actively start searching for with our current and next-generation observatories. And so, we're left with a final, profound question. This framework paints a picture of a universe that's in constant flux, a seamless transformation from the infinite possibilities of the quantum world into the concrete reality we all experience. So if reality is a process, not a state, if it's a verb, not a noun, what does that make us, who observe and participate in this cosmic unfolding? Now that is a question that physicists, philosophers, and all of us are going to be contemplating for a very, very long time.